combination with variable speed technology, like the VFDs we're going to cover in today's video, they make your entire HVAC unit more efficient, saving you and your customers money. If you want to learn more, Danfoss has several e-lessons and case stories for you to check out. You can find links to those in the video description down below. VFD stands for Variable Frequency Drive, and they look something like this. You might also hear them referred to as AC drives or variable speed drives, and that's because they are used to control the rotational speed of an AC motor. We find AC motors and VFDs used in all industries, but especially HVAC. For example, we can find them used to control a compressor's speed in a refrigeration system, and that allows us to closely match the cooling demand, which will result in significant energy savings. Traditionally, we would have had to use a fixed speed compressor. Now these simply just turn on and off, and that results in poor control and high inrush currents. We also find them used to control things such as pumps and fans in HVAC systems to allow us to unlock energy savings and improve performance and control. The VFD unit is connected into the motor's electrical supply. The unit can vary the frequency of the electricity being supplied to drive the motor, and by varying this we can control the rotational speed of the motor. Therefore, we have our variable frequency drive. To understand how a VFD works, we first need to understand some fundamentals of electricity. There are two types of electricity, and the first one we're going to look at is DC, or direct current. This is the simplest type, and we get this from batteries, solar panels, etc. You can think of DC like a river, with a current of water flowing in just one direction. With DC, the electrons just flow in a single direction. Now I'm animating this using electron flow, which is from the negative to the positive, but you might be used to seeing conventional current, which is from positive to negative. Electron flow is what's actually occurring. Conventional was the original theory, and it's still used widely today. Just be aware of the two theories and which one we're using. For electricity to flow, we need to complete the circuit. The electricity will then always try to get back to its source. When we use an oscilloscope to look at the electrical waveform of DC, we get this flat line at the maximum voltage in the positive region. If we cut the power, the line drops to zero. If we turn it on and off repeatedly, then we get a square wave pattern between 0 and maximum. If we pulse the switch to open and close over different lengths of time, then we would get a pulsating pattern. The other type of electricity is AC, or alternating current. This type is what you'll get from the outlets in your homes and places of work. With this type of electricity, the electrons within the copper wire constantly reverse and flow forwards, backwards, etc. You can think of this type like the tide of the sea, which flows in and out between two maximum points, the high tide and the low tide. If we followed the copper wires back to the generator, the wires are connected to some coils of wire which sit within the generator. Inside a basic generator, we find a magnet at the center which is rotating. The magnet has a north and south pole, or you can think of it as a positive and negative half. The electrons in the wire are negatively charged, and as you may already know, magnets push or pull depending on the polarity. As the magnets rotate past the coil, the positive and negative half are going to therefore push and pull the electrons within the copper coils, and these will also move them through the connected copper wires. The magnetic field of the magnet varies in intensity, and we can actually see the magnetic field lines by sprinkling some iron filings over a magnet. So, as the magnet rotates past the coil will experience a change in intensity of the magnetic field, and this will be from 0 up to its maximum intensity, and then as it passes the coil, it will decrease again back to 0. Then the negative half comes in and pulls the electrons backwards with the same change in intensity. Each full rotation of the magnet will therefore produce this wave pattern known as a sine wave. The voltage is not constant in this type of electricity. Instead, it repeatedly moves from 0 up to its peak, then back to 0, then through the negative peak and finally back to 0 again. Frequency refers to how many times this AC sine wave repeats per second. In North America and a few other parts of the world, we find 60 Hz electricity at the outlet. Now this means that the sine wave repeats 60 times per second. And as each wave has a positive and a negative half, this means that the polarity will therefore reverse 120 times per second. In the rest of the world, we mostly find 50 Hz electricity. So the sine wave therefore repeats 50 times per second, and therefore the current reverses 100 times per second. We also have single-phase and three-phase electricity. With single-phase, we have a connection to just a single phase of the generator, so we have therefore just one sine wave. But with three-phase electricity, we have a connection to all three phases. The phases are coils of wire which are inserted into the generator 120 degrees apart from the previous. This means the coils experience the peak of the rotating magnetic field at different times. This gives us our three phases, each with a different sine wave slightly out of sync from the previous. Remember, electricity wants to get back to its source to complete a circuit. As the current is flowing forwards and backwards at different times in each of the phases, we can essentially connect the phases together and the current will move between the different phases as the polarity of each phase moves forwards and backwards at a different time. Any excess will flow in the neutral back to the source if needed, and that's only if it's unbalanced. With single phase, we have these large gaps between the peaks, but with three phase, these can be combined to fill in the gap and therefore deliver more power. In North America, you'll also find split phase systems in residential installations. Now these have two hot wires and a neutral. This is a single phase supply which is just split in half at the transformer. We've covered that in great detail previously. Do check it out, links down below. We install the VFD into the power supply of an AC motor. This is usually a three-phase supply for most applications. Now I'm going to colour these phases in red, yellow and blue, simply because I think it's easier to see. But each country uses a different colour code, just be aware of this. The three phases enter the VFD and connect to the rectifier. The rectifier consists of multiple diodes connected in parallel. Diodes only allow electricity to flow in one direction and block it coming back in the opposite direction. As AC flows forwards and backwards, we control the path it can take, and this gives us a rough DC output. The rough DC electricity now flows into the second part, which is the DC bus. This is the filter that uses capacitors and/or inductors to smooth out the rectified DC into a clean, smooth, constant DC voltage. It does this by releasing electrons during the gaps to smooth out the ripple. The now smooth DC then flows into the final section, which is the inverter. The inverter consists of a number of electronic switches known as IGBTs. These open and close in pairs to control the flow of electricity. By controlling the path which electricity takes and how long it flows in the different paths, we can produce AC electricity from a DC source. Let's have a look at that now in detail. We will consider the first part of the VFD, which is the rectifier. In this part we find 6 diodes in parallel. I'll title these 1 to 6 as follows. Each of the 3 phases is connected to one pair of diodes. As we know, electricity needs to get back to its source to complete the circuit. So in this setup, the current will flow through the load and back to the source using another phase. Remember, it can do this because the current in each phase flows forwards and backwards at a different time. We'll see this in detail in just a moment. The load can be anything, a lamp, a motor, or an entire circuit. In this case, it will just represent the rest of our VFD circuit. The electricity will continue to alternate in the supply phases, but the diodes will only allow the peak phase to pass and will block the others. So I'm just going to animate these ones. Okay, let's see this in action. Phase 1 is first. This comes in and can only flow in one direction, which is through diode 1. It then passes through the load. Once the current passes through the load, it will then need to get back to the source, and as phase 2 is in the negative half of its cycle, the current will flow through diode 6 into phase 2. In the next segment, we see the current is still flowing in phase 1 and diode 1, but now phase 3 is in its negative half. So the current switches and the flow returns through this phase via diode 2. In the next segment, phase 2 is approaching its peak, so the current now flows through this phase and through diode 3. It then flows through the load and back into phase 3 via diode 2. In the next segment, the current flows still in phase 2 via diode 3, but phase 1 is now at its negative peak, so the current will flow through diode 4 back into phase 1. In the next segment, we see that phase 3 is now approaching its positive peak, so the current flows through this phase via diode 5. It then flows through the load and then returns via diode 4 into phase 1. Finally, the current flows through phase 3 via diode 5, through the load and then back into phase 2 via diode 6. This cycle just repeats constantly like this. The oscilloscope for the 3-phase supply will see 3 sine waves for the AC electricity. But the oscilloscope on the load will see this as a rough DC electricity with some ripples in it. Now we need to smooth out those ripples to clean up the DC electricity. For this, we connect a capacitor across the positive and the negative. This capacitor is like a storage tank and will absorb electrons when there is excess, and it will inject electrons when there is a reduction. This will therefore smooth out the ripples in the DC electricity to a nice smooth signal on the oscilloscope. We have covered capacitors in great detail previously. Do check that video out, links down below. Now that we have clean DC, we're ready to turn that back into precisely controlled AC at variable frequency. And for that, we need an inverter. An inverter is basically a number of IGBTs, which are switches that can turn on and off super fast. I'm going to animate this using some simple switches instead of IGBTs, just to make it easier to visualize. I'll number these switches as follows. To get our 3 phases, we need to open and close switches in pairs to direct the flow of current from a supply and a return path. That way the connected motor will experience alternating current. Remember, AC is where the current reverses. So if we took a lamp and connected it to some switches and a DC power source, we can control the direction of current through the lamp by opening and closing switches in the right order. Therefore, the lamp experiences alternating current even though it's coming from a DC supply. For the 3-phase supply, we time the switches to simulate the 3 phases. Let's see how this works. First of all, we close switches 1 and 6. This will give us phase 1 to phase 2. Then we close switches 1 and 2. This will give us phase 1 to phase 3. Then we close switches 3 and 2. This will give us phase 2 and phase 3. Then we close switches 3 and 4. That will give us phase 2 and 1. Then we close switches 5 and 4, and this will give us phase 3 and phase 1. And finally, we close switches 5 and 6, and this will give us phase 3 and phase 2. This cycle repeats again and again like so. If we check this with the oscilloscope, we now have a pattern that looks like AC sine wave, although it's just a little bit square. This will work fine for some applications, but not all. So how can we improve this? Do you remember earlier in the video, I said we can open and close the switch at different speeds and durations to change the waveform? Well, we can do that with this too. What we do is use a controller to rapidly open and close the switches multiple times per cycle in a pulsating pattern, each pulse varying in width. This is known as pulse width modulation. The cycle is broken up into multiple smaller segments. Each segment has a total amount of current that could flow. But by rapidly pulsating the switches, we control the amount of flow occurring per segment. This will result in an average current per segment. and we can see that this increases and decreases, thus giving us a wave pattern. The load therefore experiences a sine wave. The more segments we have, the closer it will mimic a sine wave. We can control the output voltage by controlling how long the switches are closed for. So we could, for example, output 240 volts or 120 volts just by trimming the opening and closing times. We can control the frequency by controlling the timing of the switches. So we could, for example, output 60 Hz, 50 Hz or 30 Hz, whatever is needed for the application. Remember, by controlling the frequency, we control the rotational speed of the motor. So coming back to our VFD circuit, we're going to use the controller to rapidly open and close the switches to vary the output frequency and voltage. So by combining the rectifier, the filter and the inverter, we therefore get our variable frequency drive. And this is what is used to control the speed of electrical motors and unlock